Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to sensors and transducers, and we'll extend our discussion on density measurement. And in this video we'll discuss another method of density measurement of a liquid in a container, and this will be using a combination of Bourdon tube, pressure gauge and inductive sensor. Okay. So again, the operating principle is the same as we discussed in the previous video, which was using bellows and a capacitive sensor. Bellows was used as a pressure sensitive element, pressure sensor, and capacitive sensor was used for level measurement. So the principle is the same, is that the pressure exerted by any liquid which is placed in a container at a certain height and of density rho, it is given by this: PL is equal to rho GH. So here the main concept, the main principle is that we are using two sensors. First we are using Bourdon tube. Let me use a different ink. Okay, we are using Bourdon tube as the pressure sensor, and we are using the inductive sensor as the level sensor. So we have got this value using the Bourdon tube, and we have got this value using the inductive sensor. Now G is constant, it is known, acceleration due to gravity. So we can calculate the density rho by PL by GH, this. Now the thing is that we can use any combination. It is not compulsory that you have to use capacitive sensor with bellows or Bourdon tube and inductive sensor. Any combination is acceptable. It is just that you have to use a particular level sensor and you have to use a particular pressure sensor. You can use bellows, Bourdon tube, diaphragms, capsules, membranes, anything to measure pressure. And you can use any sensor, level sensor, like capacitive, inductive, LVDT, piezoelectric, magnetostrictive, potentiometric, any level sensor you can use. It is just that I am using I'm using different combinations so that you can get an overall idea of all the sensors, level sensors and the pressure sensors which are combinedly used. Okay, any combination is acceptable. Now we have discussed Bourdon tube and we have discussed inductive sensors separately. So in a quick way we'll go through it. So Bourdon tube is basically a mechanical transducer. It is a primary transducer. Again, primary transducers are those which convert the physical parameter which is sensed by that element into mechanical movement, to and fro displacement, mechanical motion, linear motion or angular motion. So it has to be converted into suitable voltage or current signal using secondary electrical transducers. It can be anything: potentiometric, capacitive, inductive, LVDT, anything. So generally the C-shaped Bourdon tube or the oval shaped Bourdon tube is used. So as the name suggests, the design of the Bourdon tube, it is in the form of a C shape, okay, with a fixed end which is the connecting point, which is placed in contact with the source of pressure, and then we have a movable end. Movable end is connected to the secondary transducer as a pointer scale arrangement. Now special metallic alloys or elastic materials, rubber, plastic, it is used for the design of Bourdon tube. So here there are certain things which are very important. So let us say this is the Bourdon tube, First, this is the free end, this is the normal position, okay, when it is not subjected to any pressure. So here the angle A which this free end makes with the fixed end, that is important. Then when it is subjected to pressure, as a result of the pressure difference between the external, means outside the tube, and inside the Bourdon tube, this free end or movable end, it tries to elongate, tries to stretch itself, and as a result a kind of movement, angular movement of this free end happens. So let's say it stretches itself and moves to this position. So here from the center, the angle which this free end makes with the fixed end, that is B, and the difference between these two angles, that is C. Then we have capital R, which is the radius from this center on the tube in the normal resting position, and as a result of this there are certain mathematical calculations which give us relationship between the displacement of the free end due to deformation or pressure difference and the differential pressure. So it is given by the ratio of the angle C by A. C, which is the difference between the initial angle and the final angle, which is equal to delta P, which is the pressure difference between external and internal, outside and inside the tube, that is equal to 1 minus mu square EBT R square into 1 minus B square by A square into alpha by beta plus psi. So here the radial displacement, that is given by C by A into R into 1 minus cos A, tangential displacement, that is given by C by A into R into A minus cos A, and the total displacement of the free end is root over of radial displacement squared plus tangential displacement squared. So these are the parameters. As I said, delta P is the pressure difference between the external and internal side of the tube. R is the radius of the arc of the Bourdon tube, as I specified, R, capital R. Mu is Poisson's ratio, which is the ratio between lateral and longitudinal strain. E is the Young's modulus of the material. A is the semi-major axis of the tube and B is the semi-minor axis of the tube. So this tube, the semi-major axis, this A, and semi-minor axis B, okay. And then we have T is the thickness of the tube, psi is RT by A square, which is a dimensionless constant which is unique for a particular material and dimension of the tube. Alpha and beta, again dimensionless constants depending upon the material which is used, and ABC are the angles which I specified. A is the initial angle, B is the final angle, C is the difference between them. So this gives us the relationship between the angle and the differential pressure. As these things are already known, we can calculate the differential pressure. This is about the pressure sensitive element which we have used in this case, which is the Bourdon tube. Next we have is the inductive sensor. Now the inductive sensor, again it is based on the principle of self-inductance. So it can be used for measurement of various parameters. In this case we are trying to measure it for calculating the level. So in a way we are trying to measure displacement, okay, change in position. So basically it consists of a core, a ferromagnetic core, semicircular shaped, armature, rod shaped. The core has number of turns of wire, the voltage source, and the armature is movable, okay, it is free to move while the core is fixed. So here the concept of reluctance comes into play. Reluctance is the in opposition to flux which the inductive sensor it shows, okay. So here the reluctance of this sensor is dependent on the three parts. First, the core reluctance, second the armature reluctance, and third and the most important, which is the air gap reluctance. Now here the core reluctance is fixed because it is dependent on all the fixed parameters. I have already discussed it in inductive sensor in detail, so here I am not unnecessary, I am not stretching it. The core reluctance is fixed and the armature reluctance is fixed because it is dependent on the parameters that are involved here. They are all constant, they cannot change. But the air gap reluctance, with this d involved, where d is the air gap distance, which is the separation between the core and the armature, this air gap, okay. So when this armature, which is connected, in this case it will be connected to the float and rod arrangement, which is connected or which is placed on the surface of the liquid, this core, the armature, it moves up and down, okay. The armature, which is connected to the float and rod arrangement, it moves up and down. So as it moves up and down, the air gap distance, it changes. So as the air gap distance, it changes, so the reluctance of the air gap, that also changes, which is given by 2d by mu 0 pi r square, okay. So here these are the parameters. N is the number of turns of coil, r is the radius of the arc of this semicircular core, T is the thickness, D is the air gap, and R is the internal radius, okay, of this core and this tube, which is the armature, rod shaped internal. So here, as the air gap reluctance it changes, the total reluctance also changes, because everything here is fixed, only this is fixed, this is fixed. So only this air gap contributes to change in total reluctance, because this is variable, okay, this is variable. So the sensor inductance, it changes as per this relationship, that is n square, where n is the number of turns of coil, divided by the total reluctance, which is dependent on the air gap reluctance. So in a way, the sensor inductance is dependent on the air gap reluctance, which is dependent on the air gap, okay, the air gap distance, okay. So the whole thing, it is designed as per this. First, we have the liquid in container, and we have the Bourdon tube, which is connected, the source where it is connected to the liquid column, that is connected to that end, and it measures the liquid column pressure, okay. And the inductive sensor, that measures the height or level of the liquid. So it can be done in various ways. This is one arrangement. In another arrangement, what can be done? A series of inductive sensors can be placed along the walls of the container. So whenever this float or rod, it moves up and down, this rod, it strikes the movable armature. As a result, it gets displaced from its initial position, and the air gap distance, it changes, and that gives us the value of the level of the liquid at a certain position. So as a result of all these two sensors, we get the data related to the liquid column pressure and the height of the liquid. And from this, we can calculate the density rho, which is given by PL by GH, because PL is calculated using the Bourdon tube, H is calculated using the inductive sensor, and G is already known. It is a constant, 9.8 meter per second square. Here one thing has to be taken care of, which is that if this liquid container is open without any covering, any lid, so the atmospheric pressure will also come into play. So here the pressure sensor, it measures both the liquid column pressure and the atmospheric pressure. So in order to get the liquid column pressure, we have to subtract the atmospheric pressure from it, which we can get easily, and from this we can get the density using this relationship. And if it is closed, then there will be no atmospheric pressure and the sensor reading directly gives us the liquid column pressure. So this is when it is open and this is when it is closed, because when it will be closed, the atmospheric pressure will have no role to play. Okay, so this is the basic principle of density measurement using Bourdon tube and inductive sensor. Bourdon tube for pressure measurement, inductive sensor for level measurement, liquid level measurement. Okay, so let us try to understand this whole concept from a three-dimensional perspective. So this is the Bourdon tube pressure gauge. So this fixed end, the connecting point, is connected to the source of pressure. So because of the pressure difference between the inside and outside the tube, this whole thing, the free end, it tries to elongate itself, to stretch itself. So as a result of this, the free end connected to this rod, it moves, and that connected to a pointer scale arrangement or a secondary electrical transducer, that gives us the pressure reading. Then the float and rod connected to the inductive sensor or the armature, the movable armature, when the level of the liquid in the container it changes, this thing, it moves up and down, and as a result the air gap distance, it changes. So as the air gap distance it changes, the inductance of the sensor, that changes, and that produces a suitable voltage signal as per Faraday's law, which is V is equal to L di by dt or N d phi by dt, Faraday and Lenz's law. So here we have used Bourdon tube for pressure measurement and inductive sensor for level measurement. So once we have got the parameters, that is the level H and the liquid column pressure, we can easily determine the density by this. Okay, this. Now again I remind you that it is not compulsory that if you have used an inductive sensor then you have to use a Bourdon tube. There is no such thing. You can use any level sensor of your choice, you can use any pressure sensor of your choice, but in some cases because of the operational requirements, certain combinations are selected based on whether one sensor operation interferes with the operation of the other, like that, you know, in terms of shape, size, or any other signal interference, like that. Also cost requirements. If the cost of one sensor goes up and it is compulsory to use that sensor, then we have to use another sensor which is cost effective. So that also, you know, drives the choice of what combination of sensors should be selected for a particular measurement technique. So there are a lot of things, but you're free to use any sensor of your choice. Okay, so this is density measurement using Bourdon tube for pressure measurement and inductive sensor for level measurement, and from that we calculated the density as per this relationship. Okay, so I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.